Okay, I'm working 13.7, which is surface integrals, and going to be starting with number 5. So we're asked to find the surface integral over the surface S of x plus y plus z with respect to surface area, where S is the parallelogram with the parametric equations x equals u plus v, y equals u minus v, and z equals 1 plus 2u plus v. U is between 0 and 2. V is between 0 and 1. All right, so I'm going to convert the parametric equations over to the vector form r of uv. So my surface S can be drawn with this. So that means it can be drawn with this vector form of this surface. Okay. And we're trying to find the surface integral. Now this right here is a linear function, which means, scalar function, f of x, y, z. So I'm trying to find what this is. The surface integral over the surface S of a scalar function with respect to surface area. So if you go to the formulas that were provided to you in class, let me write the formula up here since it's the first time I'm doing one of these. Give me just a second here. All right, yeah, so I'll do it exactly the way I did it there. So what we're going to do is we're going to convert this into a double integral over the region D. Now D comes from our restrictions on our u and v, okay? That's going to give us our limits of integration. It will be our scalar function evaluated at the vector function. So we're going to take the vector components, the components x, y, and z, and we're going to replace them into the scalar function. Then we're going to multiply that times the magnitude of the cross product of the partial derivatives of r with respect to u and v, respectively. And then this will now be with respect to area. So this right here is this. And then this right here is just the function evaluated. So I'm going to need some stuff in order to do this problem. I'm going to need quite a few things. So let me get some partials here and then cross them and then take the magnitude, and then we should be ready to roll. So I'm going to take partial of r with respect to u is 1, 1, 2. Partial of r with respect to v is 1, negative 1, 1. And then I cross these, so r, partial of r with respect to u, cross with partial of r with respect to v. Let's see, we've got 1, take away negative 2, so 1 plus 2 is 3. So we've got 3 minus 3. And then now let's do this one. So 1, take away 2, but then that's negative 1. But then it's the middle one, so I switch the sign, so it's 1. And then here I've got negative 1, take away 1, which should be negative 2. So our cross product of the partials should be that vector. Before I get too far, I'm just going to double check it. Yep, okay. And now we need its magnitude. So the magnitude of this is going to be the square root of each of these squared and added together. So 9 plus 1 plus 4. That's going to be root 14. That's just a constant, so we got lucky. We're going to be able to pull that constant out of the double integral. So I was just about to erase that. I need it. I don't need this. I'll keep my restrictions. So this becomes double integral over d of Now, the scalar function, which was this one, replace the x with this, the y with this, the z with this. So it's just going to be u plus v, that's x, plus u minus v, that's y, plus 1 plus 2u plus v, times root 14 with respect to area. Let me clean up the inside of that there. And I'm also going to put my limits of integration on here. I'm going to go 0 to 2, 0 to 1. That means I'm going to have on the outside du and then on the inside dv. Let's see, u, 2u, 4u. V minus v cancels. So I just have a v and then a plus 1. So I get plus v plus 1. Root 14, I pull that out. And then d, like I said, v du. And in an effort to save us time, I'm going to trust that you can do that and just give you the results. This should be 11 root 14. All right, that was pretty straightforward. They gave us the vector, the surface. They gave us the limits of integration. We were in business. All we had to do is just kind of evaluate the cross product, take its magnitude, plug everything in and go. So let's see where these start to get a little messy. Number 7, they give you, again, they give you the all the information you need, so I'm going to let you do that one. I'm going to do number 9. So 9 is different because they give you the surface integral they want you to evaluate. They want it to be x squared yz with respect to surface area. They say that S is part of the plane z equals 1 plus 2x plus 3y. That lies above the rectangle 0, 3, 0, 2. So this is the definition here of S. So what we know is we have a plane here, right? Sitting here in three-dimensional space. If we look at the ground, this is on the ground 0, 3 to 0, 2. We're looking at the plane just above this, okay? So wherever the plane is, just that one little rectangle mapped into the plane, that's the surface we're integrating with respect to, okay? We're not trying to find the area, that was last section, but that's the surface of integration. So we need to find some vector function which will draw that. But we notice that this is some function. I can call it f. I think in the notes I call it, let me see, in the notes do I call it g? This is a special case. Yeah, I call it g. Yeah, so I call it g because we're calling this right here our scalar function f of x, y, z, so we don't want to use f twice. So g of x, y, right, is equal to square, I have no idea why I just put a square root there. And I just got a text message, so let me see what that's all about. This is just 1 plus 2x plus 3y. Let me just check my phone real quick. Software update. Okay, now, if we can write our surface S in terms of x and y, all right, if the z coordinate is in terms of x and y, then what we have is that the magnitude of the partial, right, the cross product that we do, these partials, here it'll be in terms of x and y instead of u and v, that this turns out to be with the formula 1 plus partial g, I'll say partial g with respect to x squared plus partial g with respect to y squared. So that should look very familiar from last section. So let me go ahead and put that in. Partial of g with respect to x, which is this, is 2, and then square it, so we get 4, plus partial of g with respect to y is 3, but then square it, so we get 9. So do we get root 14 again? We do. Okay, coincidence. So what we need to remember is this is a special case. What's happening here is that x is just x, y is just y, and z is the function of the two. So when I come up here and I'm trying to convert this over, double integral over d, d is going to be controlled by these, this is my restrictions on x and y. The scalar function evaluated on s means I'm just going to replace x with x, I'm going to replace y with y, and I'm going to replace z with this. So that becomes x squared times y times z, which is 1 plus 2x plus 3y. And then I have times this, which is this, so times root 14. I can pull that out. And then dA. All right, so please understand, this is the same formula from last time, with the exception that this computation right here is easier, and that when you plug into the scalar function, we're not plugging in functions of u and v, we're plugging in functions of x and y. It's just because the nature of the special case here. All right, so now this becomes, let's see, root 14. And then I can use my limits here, 0 to 3, 0 to 2. You could distribute this through if you want. X squared y plus 2x cubed y plus 3x squared y squared. So I distributed that through. I took my root 14 out, and then this is going to be dy dx. Let me just make sure I've got that all set up properly. X squared y, 2x cubed y, 3x squared y squared. 0 to, where are we? Y squared. 15. Okay, yeah, so again, I'll let you work this out. This is a double integral, pretty clean. This should turn out to be 171 root 14. All right, let's look at number 11. Although 10 looks kind of interesting. Let me try and set up 10 quickly. Okay, so for 10, you have a surface integral of, let's see, xz with respect to surface area. And S is the part of the plane 2x plus 2y plus z equals 4 that lies in the first octant. So if we're going to be in the first octant, we need to figure out where that plane comes in and cuts through. Probably it's going to be something like this. You know, we have like almost like a tetrahedron looking thing when that plane cuts through. So I'm going to try and just figure that out first. To do that, I let z be 0. If z is 0, then I get 2x plus 2y equals 4. That's x plus y equals 2. that's y equals negative x plus 2. So if I draw this in the xy plane on the ground, up 2, and then it's down 1 over 1, down 1 over 1, so it's going to hit here at 2 also. That's where my plane hits. So I'm just looking at the surface, the plane above that, right? And where does it hit the z? At 4? Hits here at 4, hits here at 2, hits here at 2. So this is my surface S. I can control that surface, or I can actually draw that surface pretty easily. You know, if I look at this down on the ground as a type 1 region, my x is between 0 and 2. My y here is between 0 and this line. That line is this, so negative x plus 2. And I should be okay to use a special case here, because my z coordinate, I can solve this for z. Like that. And now my z is a function of two variables, so this gives me my special case. So I can use that shortcut. So when I go and I convert this into the double integral over d of what? F of x, y, z, I'm just going to remember that because this is a special case, x is just x, y is just y, and of course z is this. So when I go to rewrite this, x will just stay x. Z will turn into this, so negative 2x minus 2y plus 4. But then the next part is the square root, so this is the shortcut part, of 1 plus the partial of g with respect to x, which is negative 2 squared, so 4, plus the partial of g with respect to y, which is negative 2 squared, which is 4 again, and then dA. And where's my little cloth? There it is. And this becomes, let's see, double integral. Let's see, we can put the limits of integration in here, 0 to 2, and then 0 to negative x plus 2. What is that? Root, that's 8, 9. Hey, that's a 3. Let me pull the 3 out. 3. And then distribute through here, we get negative 2x squared minus 2xy plus 4x. And I'm going dy dx. I have to use that order because this was like a type 1 region. So we're looking at trying to evaluate this double integral. Is this number 10? 3, 4, 8, minus 2. dy. Yes, that's all good. And then I'll let you work the rest of this out. This should equal at the end of it all 4. Maybe I have time for one more right now. I think 11 is similar to 10, except that you have to come up with the equation in the plane first. It's going to take a little more work. Let's look at number 13. I am recording, right? Yeah. Which one did I say I was going to do? 13? Surface integral x squared z squared ds, where s is the part of the cone, z squared equals x squared plus y squared. That lies between the planes z equals 1 and z equals, where's it, 3. All right, now let me get a picture of what's going on here. What does my S look like? Well, it's this cone, which looks like this. Actually goes the other direction too, like that. However, we're just looking at the surface that is cut off between z equals 1 and z equals 3. So if we imagine just coming through and slicing this, raising up off the ground 1 unit, slicing it, we'd slice it here somewhere. Raise up to 3, we'd slice it here. This one's kind of easier to draw. This is just going to give us this surface, right, is what we're integrating over. So this is our S. So the question is, can we come up with some sort of representation of this surface? Well, because I'm only on the top part, I don't need to consider the bottom part. I can look at this as being the square root of x squared plus y squared. That's what z is. And in that case, z is a function of x and y. Also, when I look straight down on this, right, when I look from the top, the region on the ground, the xy, the region that my surface is casting a shadow onto is this region, you know what, nope, that's not correct. Let me back that up. Why can I not keep that darn thing? Let me do it this way. Okay, so we have, if you look at this going to the ground like that, and I'll take this part out, then we get on the ground our region of integration is going to be a polar region. My question is, do we want to go get that now? I guess we could. Let's try and figure out where this hits the ground. So what we want to know is, how wide this is, right? So I want to know when that cone hits the z equals 3. So when does this cone equal 3? So when does square root of x squared plus y squared equal 3? Well, you square both sides, you get x squared plus y squared equals 9. And so it's going to hit at a circle of radius 3. So that was correct for me to assume that this was 3. And then if I do the same thing, I say, where does it hit this plane z equals 1? I make a 1 here, square both sides, I get 1. So this would be a circle of radius 1. So the inner piece is 1 here. All right, but let's get down to business here. This is just setting up like my restrictions in determining I'm going to go to polar at some point. I want to see if this is a special case. So can I convert this over? And we can see it is, right? Z is a function of x and y. So this is my g of xy. So just remember that x will be x here, y will be y, and z will be this, right? Z will be this. So this becomes a double integral over some region D, which is this, of x squared, so it's just x squared, times z squared. So z is actually this, and if I square it, I get x squared plus y squared. That's really nice. And then I need to come in and get this, this special piece right here, which is the square root of 1 plus the partial of g with respect to x. So taking the derivative of this root. We did that earlier in a different problem. It was this thing over square root of x squared plus y squared, but then we had to square it. And then we did the same thing on this one. It was y over square root of x squared plus y squared, and then we had to square it. And then we have dA. All right, now, when we did this earlier and squared it, I don't know if you remember, it turned into root 2. So I'm going to just write a root 2 on the outside. And then I have x squared times x squared plus y squared. I do realize I could distribute that through, but I'm not going to because I'm about to convert this to polar. Because I can't get restrictions that are nice on x and y. That's a good polar region. So converting now to polar, I know my theta is going to be between 0 and 2 pi. I know my r is going to be between 1 and 3. Be careful here, 1 and 3. And so this becomes root 2 integral 0 to 2 pi integral 1 to 3. Okay, x squared plus y squared in polar is r squared. And x squared is r cosine theta squared, which becomes r squared cosine squared theta times r squared, times an r that we have to insert because of polar. So I should have r to the 5th cosine squared theta dr d theta. And I got my root 2 out there. Just double check this. Root 2, 0 to 2 pi, 1 to 3, r to the 5th cosine squared. That's all good. Working that out. By the way, you could split this into two integrals and multiply them because r is isolated and theta, the function of theta is isolated, or just work it out normally. They're giving me something like 364 root 2 over 3 pi. All right, that's number 13. I'll do more of these later.